be honest, who here hasn't tried to Google an integral for their math homework before? Well, no fear, no shame, because many of the world's finest engineers and physicists have also been stumped by integrals. Maybe they aren't the ones on your high school calc midterm, but they pertain to some of the most unsolvable problems in chemistry, quantum mechanics, and even finance. The solution is the Monte Carlo method. In order to explain this, let me first take you to the casino. Don't mind that Polish guy over there playing solitaire. He's got a bit of the flu. Say, I give you $1 million if you can find the area of this target. The rules say you get unlimited darts, you get to know the area outside the target, but you are not allowed to measure it. If your first guess is to stab me with the darts and run with the money, let me first give you a better solution. Try blindly, or for our case, randomly, shooting darts at it. If you were to count the number of darts in the bullseye and divide by the total number of darts, you can get an approximation of the target to board area ratio. So let's scale up. See the simulation where you have 1,000 random computer-generated darts shot at the square region. If the quadrature of the coordinates are less than 1, they're colored red. Greater than 1, they're black. Repeating our calculation from before, we get that the area is 3.149, which I think is pretty darn close to pi. Generalizing this technique, it's called the Monte Carlo integration method, where the area under the function can be described by the percent random points that are within the function's constraints. Typically, these methods are used for high-volume integrals commonly present in quantum and classical mechanics. These two lenses of physics take nearly a similar mathematical form, e to the sum energy function over a population, to determine the average energy of a state. In classical mechanics, we can mathematically describe the motion of a molecule based off of how it rotates, vibrates, and moves using a partition function. If we can determine the energy of a molecule from this motion, you can find the average energy in a larger system. The average, which is given by the sum of the probability of any given energy. So, how is this done in quantum mechanics? We must first describe a particle's quantum motion using a wave function psi. The energy of the particle can then be calculated for using Schrödinger's equation, which states h psi is equal to energy psi, where h is the Hamiltonian, or a mathematical description of the kinetic and potential energy of the particle. So, how would you calculate the average energy then? Well, if you were to integrate the entire space a particle could exist in and use the quantum mechanic definition of average, which is the integral of psi times some operator psi, then we can build this integral by a reflection. And now maybe we can consider how Monte Carlo integration is starting to creep up on this integral. The fact is, we never really know our wave function psi. Psi is really just a placeholder for describing all of the hundreds of electrons in a polyatomic molecule. So if each wave function describes the motion of an electron, and each electron lives in an atomic orbital, and every atomic orbital varies depending on interactions with other orbitals, interactions with solvents, having a bad hair day, riding a goat, getting a stomachache from eating too much Taco Bell in an alternate universe, and we still have to vary our wave function 300 more times to get a good answer. You can quickly understand why the variational method, the process of getting a quote-unquote accurate wave function by changing and tweaking parameters, can take a really long time, even for the fastest supercomputer. Similar to approximating the area of a circle, the Schrödinger equation can be solved using variational quantum Monte Carlo. We can use random sampling to vary a trial wave function. So instead of counting the probability of dots in a circle, we are calculating the probability density of electrons in a given space that can be given by this equation. While you can read more about the potential ways to improve these computational techniques, at least we can bask in the usefulness of random darts, casinos, and guessing your way out of solving an integral. Until next time!